we talked about the time domain characteristics. So what we did was we basically modeled something like an inverter with resistors. So this ended up being 2 times unit resistor for the P, switch, capacitance for the P, and then capacitance for the N. Oops, is 1C, and then a switch and a resistance of the N. Okay, and then we had a sort of the gate capacitance for the P and the gate capacitance for the N. And so remember a few things here. So we said each process has something called an R for the minimum NMOS transistor size. So this was the resistance. And if you had something twice as wide, you would end up with R over 2 for 2x wide NMOS, and so on. So it'd be R over 4 for a 4x wide NMOS. And then we said that the resistance is 2R is the minimum resistance. For a PMOS minimum. Okay, so a resistance would be R for 2x wide PMOS. And that's why we would make the PMOS sort of as a matter of course, or sort of for typical, let's say typical cases or assumptions, 1x size, and the NMOS, sorry, the PMOS 2x size and the NMOS 1x size. Okay, so to make the rise and fall times equal. So this is all we talked about, I think, the lecture before the midterm. So hopefully you guys remember that. So, this gave us, we said, this gave us a pretty accurate model, we thought, although it was a very simple model. When we compare it to simulations, it was within, say, 10% of a transient event. And by that, I mean if you had, sorry guys, if you had a situation where your input was changing and your output was going down. So this pull down, our hand model with these resistors and stuff was within, these delays, et cetera, were within 10% of what our simulations would do. So it was a pretty good model. But it's really for a single stage, okay, for just this one device, okay, and maybe the next stage you're driving. But if you have a case where you have multiple things happening, you need to figure out how to use this thing, because it's not always just 1 or 2 stages. In fact, most of the time, so basically you can end up with some complex situations. So let's take an example here, which is from the book, which is that the designer is trying to design a decoder, okay, to try this register file. And register file is just means it's just a bunch of registers, okay? So each register is 32 bits wide, okay? And there's 16 of these, okay? And so we have an input address that's 4 bits wide, okay? And we have 16 words in registers, so we need a decoder to say what goes, depending on what's here, selecting the decoder. Okay, and then it also says that each bit in the decoder, so each one of these guys, represents a loading of 3-unit transistors, whatever. So whatever, so 3 times C. So each one of these guys. Okay. So what we want to do is figure out how many stages to use, how large should each stage be, and how fast can the decoder operate. Okay. So now we've got a decoder to deal with, and here's what a decoder kind of looks like. Okay, I'm gonna, boy, this will be an interesting exercise to try to draw this thing. So a decoder looks like, hopefully this is readable for you guys. Hopefully it's not too small. But so we have these bits, A0 bar. So we have A0 bar, A0. Usually you buffer it. It's okay to do an inverting buffer. Okay, A1 bar, A1. A2 bar, A2. Okay, so these are all the, where's that? These are the input addresses, okay? So it says the inputs are the true and complement addresses of the input. So that's why I've got all these guys here. So A3 bar and A3. Okay, each one of these, we would buffer them. So I'm trying to draw the decoder here at a high level. Okay, and you would run these down. And because you have 16 words and you have a 4-bit decoder, you can basically make the decoder out of a bunch of 4-input AND gates. Because we always make NANDs in CMOS, we just put a NAND and invert it. Okay, and then say let's say in the case of the first one, word 0. Okay, this guy would connect to this dude here. Notice this is A0 here, so this would be over here. It'd be A0 bar. Okay, so that's why I'm connecting it. So this would be A1 bar. This would be A2 bar and A3 bar, and then we could, there'd be 16 of these guys. Okay. And this guy would be connected to here, 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 and here. So this guy would get selected if we've got all zeros. Because all zeros would mean it'd be inverted, so it'd be 1, 1, 1, 1. You'll get a 0 out here, and word 0 would get selected. And this guy over here, the last guy, would get selected with all 1s, and he'd get selected. And then, so that's the decoder. That's what it looks like. And so this guy. But then we also have to worry about the fact that we're driving, each line has 32 bits, and each one of them has the capacitance of 3-unit transistors. So we'll have this capacitor that the inverter needs to drive. So here we've got, so now, we got the timing of this A0, this inverter here. We got to size that a certain way. We got to size this NAND gate a certain way, and the inverter to be able to get as fast as possible to drive this 32 by 3 unit transistor size here. Okay, so in other words, it's a complicated scenario to try to use. This is just basically telling us how to optimize or how to get timing for a single stage. But when we have multiple stages, whoops, when we have multiple stages, we've got an issue, okay? So basically we come up with this method, and this is something that's commonly used, called, well, it's called a logical effort, but let me actually just run this like this so that's, let's see, how do I run it? Okay, let's see. How do I, attachment, slideshow. Can I draw? Yeah, I guess I can still draw on this. That's cool. Okay. Okay, so we want to basically express the delay of a logic gate. This is sort of the first step we do, is express the delay of a process in process independent units. Okay, so the first thing we do is we define this delay, which is the absolute value of the delay divided by this time constant in the process. And this time constant is defined as 3RC. Okay, so I looked up, if you actually go to our book, and there's a table in chapter 8 that gives a bunch of R and C values. So these are the same R and C values we talked about in that simplified model of the gate. Okay, and so the R in the 180 nanometer TSMC process, which we're in, is, I just read that at 2.4 kilo ohms per micron of transistor width. This is for NMOS. Okay, and the diffusion capacitance ends up being around 1.5 femtofarads per micron of width. Okay, so this, this is supposed to be for minimum size. So for a minimum size, it doesn't really matter, but for a minimum size device, just remember this is per micron. But again, because RC won't matter, because for a minimum size, if we do the RC, so R min times C min, so I think the minimum size transistor is like 300 nanometers wide, if I remember correctly. So let's say roughly a third of this size. So R will go up by a factor of 3, because the minimum size transistor is 3 times smaller. So this will go up by a factor of 3, but then the capacitance will go down, so that times the capacitance, and that will go down by a factor of 3. So either way, it doesn't matter. You're just talking about RC regardless of the value. And so I calculated this RC. It ends up being 3.6 picoseconds. Okay, so 3 RC is 11 picoseconds. Okay, so, and then, let's say if we had a 65 nanometer process, the 3 RC would be 3x faster, maybe somewhere between 3 and 4x faster than we are if we were in a 600 nanometer process. It would be 6 times longer, okay? But because we're doing the absolute delay of whatever stage we're calculating, we're dividing that by this RC for a particular process, we're ending up with this process independent delay. So everything's going to be given in terms of D, okay? So this process independent delay. And then when you're done with it, you will get something in units of D, and no matter whatever process you're in, you multiply that by the tau of that to get the absolute resistance. Okay, so that everything's given in that form, and then the delay is then for each gate is given as two components. Okay, F and P. Okay, F is called the effort delay. Okay, not quite sure why. And again, it has two components. Okay, this effort delay means how much effort this gate has to do to drive an output. Okay, so it has two components. The first component is called the logical effort. Okay, and so sorry guys, this is probably going to be the most complicated lecture in the whole class, and just going to have to bear with me. There's a lot of like these things, and it's not quite clear where I'm going with this, but just work with me for the time being. Okay, so this logical effort measures how good a particular gate is compared to a inverter. Okay, so let's say, and I'll drive this for you, derive this for you guys, but let's say G is 1 for an inverter, right? So that's our baseline. A NMOS, sorry, not NMOS, a NAND gate we decided the NAND gate has to be sized differently to have the same drive as a 1X inverter, right? For this guy to have the same rise fall times, this was 1X, 2X. So we decided the N MOSFETs here had to be 2X, 2X to be able to pull down at the same speed as a 1X inverter. Okay. So this can still be 2X and 2X. Okay. So if G is equal to 1 for an inverter, G would be 4/3 for a NAND gate. I'll show you guys how we came up with that. But anyway, so baseline for G, it's this factor G is just a function of the topology of the gate. So any NAND gate, 2-input NAND gate you would have a G of 4/3. Any 3-input NAND gate you would have a G of 5/3, because you need to make those devices even bigger to have the same drive as an inverter, and so on and so forth. Okay, so we'll talk about how you come up with different Gs, but basically that's something called a logical effort that only has to do with the topology of the gate. Okay. The second thing, so this is the components of this effort delay, this first component. The second thing is the so-called electrical effort or fan out. And that's just a ratio of the capacitive load. So let's say our 2-input NAND gate that has a G of 4/3, it's basically the capacitance that it's driving over its own input capacitance. C out over C in. Okay, and that's sometimes called a fan out. Okay, so that's the definition of G and H. So it really has to do, this first term, GH or F, it's basically has to do with how well your device is driving a particular load. Okay, if it's a 3-input NAND gate, it has a harder time driving a particular capacitance than if it was a 2-input NAND gate. And then if it was a 2-input NAND gate, would have a harder time driving a capacitance that's 10 times bigger than the same 2-input NAND gate. So that's those are the factors that we're looking at, G and H. Okay, and then the final factor is this thing called P. Okay, which is the gate's own delay. Okay, so if it's driving no load, it's, what parasitic capacitance would it have? For example, in the case of the inverter, we said the gate capacitance, you remember it's got a 2x pull up and a 1x pull down. So the capacitances would be 2C. So if this is a switch resistor, I hope I'm, whoops, sorry guys. Let me erase this thing. So let's see. So we have 2R, we have a switch, and the 2C for the, this is for a 2X PMOS. And then we had the 1C for the NMOS and a switch and R. Okay, so if there's, this is the output, okay? So if there's nothing being driven, we still have this 3C's worth of capacitance. So that's the without it driving anything else, you have this parasitic capacitance. So the upshot is, this is what you end up with, is you have a factor that represents what you're driving and how difficult it is for you to drive it, and then a factor that describes how much parasitic capacitance you have. Okay, so let's derive this for a NAND gate. Okay, and so anyway, like before I do the deriving of it, okay, let's just look at how you would use this. Okay, so if you show the normalized delay, this D, okay, as a function of H, as a function of fan out. So this is you're driving one other gate like yourself, two other gates, 3, 4, 5 other gates like yourself, okay? Because look at where the variable here is H, G is a constant given, let's look at an inverter, okay? So this is the curve for the inverter, the first one, okay? Oops, I mean, that spoils it, but so G is 1, P is 1, okay? So D is G times H plus 1, or H plus 1, okay? So let me get this right. So if you got an H of 1, how come I got a, wait a minute. No, okay, no, sorry guys, I got it. Confused myself. So H is equal to 1, you end up with a delay of 2. If you're driving 2 inverters like yourself, you end up with a delay of 3. Okay, so what I would look like is, let's say you're driving, you're an inverter, minimum size inverter, you're driving 3 inverters like yourself. Okay, what you end up with is 4D. Okay, so this normalized delay. Okay, and then let's say you want to figure out what this delay is. Okay, so if for our process, 100 nanometer process, okay, you multiply this by the 3RC value, which was 11 picoseconds. Okay, so this would give us 44 picoseconds for the delay of this guy driving 3 things like itself. Okay, and if you had a 65 nanometer process, if you remember, the tau was 3 picoseconds. And so again, the D absolute value there, if you had the same situation, you would be 4 times 3 picoseconds, oops, and you'd end up with 12 picoseconds. Okay. So that's how you'd use this, okay? So let's say this was the case for a inverter. So we got this plot, and we can see how it drives things. Okay, so let's look at a NAND gate. Okay, NAND gate, we said, has a let's see. Sorry, guys. Okay. Oops. So here's the equations for a NAND gate. So let's drive it. Okay. Let's not talk about the NOR gate, so just the NAND gate right now. Okay, so the NAND gate looks like this. Can you guys read? Can you make this out? Is it small enough or big enough for you to?
Yeah, it's fine.
Okay, great. Okay, so let's say we wanted to see a NAND gate that has the same drive as a minimum inverter. Okay, we said, let me actually move this off here. So we had our minimum inverter. So this was a 2x and a 1x. Okay, and we said if we have a NAND gate that wants to have the same drive, these two up the P MOSFETs could stay the same size, but the N MOSFETs, we had to make them twice as wide because there's two of them in series. So this has to be 2x wide, this has to be 2x wide, okay, to have the same drive. And so this is the first step in coming up with what this model looks like, okay? So you basically size it so it has the same drive as a 2x inverter, okay? And then G is how much is, you look at the input capacitance now of one of the inputs, okay? So in this case, this is 2x, like the P is 2x and the N is 2x. So the gate capacitance is 4, okay, 4C, let's say, okay? Now notice the gate capacitance for a unit inverter was 2C for this guy and 1C for this. So this is NAND 2, and C gate for the inverter was 3C, okay? And G is the ratio between these, 4/3. Okay, that's our G. So no matter what process you're in, as long as you have a 2-input NAND gate that's sized to be to have the same drive as your unit inverter, its G is going to be 4/3. So I don't know how you guys want to look at it, but it's like 4/3. Maybe more difficult for this inverter, or it provides a loading of 4/3 more for the previous stage. It just depends on how you want to look at it, okay? But just so that this is the calculation for how they come up with G, okay? And then P is the same story here. We look at looking for the parasitic delay. So we're looking at the output, and you had 2C of capacitance for the PMOS, 1C of capacitance for the NMOS, so we had 3C of capacitance on the output. Whereas for a NAND gate that's sized like that, so we have each one of these PMOSFETs has 2 Cs, okay, and because we double the size of the NMOS, it also has 2 Cs, so you end up with 6 Cs here. Okay, so your P, your own parasitic capacitance, is ratioed to the parasitic capacitance of the inverter and is 2. Okay, so this delay ends up being, again, G times H, so 4/3 H plus P, which is 2. Okay, so it gives us this higher, sharper slope curve, okay, which says that you know, if you have a, let's say, what did we say? For a delay of 4, for if you're driving 4 NAND gates like yourself, okay, so let's look at a delay of that. Because we looked at driving 4, we said 3, right? We did, yeah, I think we did 3 inverters. So let's do the same thing for the NAND gate. So this would be a 2-input NAND gate driving 3 other NAND gates like itself, okay? So we have our equation is 4/3 times H. H is 3, okay, plus 2. So we end up with 6. Okay, so we have 6D of delay. And if you want to get the absolute delay of that, we multiply that, we plug in this tau, I should say 6 tau. Let's call it 6 tau. We end up with 6 times 11 picoseconds, or 66 picoseconds. Okay, and we're going to compare that to our 44 picoseconds for our inverter delay. So you see, basically, we end up, a NAND gate will have, a NAND gate stage will have a bigger delay than an inverter stage, even when it's sort of appropriately sized. Okay?
Professor?
Yeah.
I just had a quick question. For your GNP, where did you get your 3C from again?
Sorry, for which one? For GM?
And P, yeah. Where did you get the 3C from?
G.
In the top right, when you're doing the logic drive and the parasitic, you have
This
4.
one here?
Yeah, where did you get the 3C from?
Oh, that was the equivalent input gate capacitance of a minimum size inverter.
Okay.
So each one, G is
Thanks.
ratioed. This is the inverter for that same thing, which is the gate. And this is the inverter sort of drain.
All right, thank you.
Sure. Any other questions?
So is that part always going to be 3C?
This guy?
Yeah.
Yeah, for a NAND gate sized to be have the same drive as a minimum size inverter, it would always be 3C.
Okay, thank you.
Sure. All right. Any other questions? So let me. So let's do this. So let's do this, and you guys, maybe we do it together. I'll give you guys a head start. I am assuming. Did you guys need this to be up for? Let me do this. Hold on a second. Let me stop this. Just keep that. And then can I insert new slide? And then okay. So let's say we want to figure out the same thing for a two input NOR gate. Okay. So remember, D is G times H plus P. Okay. So once you guys, I'll give you guys maybe like a minute or two head start. You guys kind of try that. See if you can come up with that. Okay, so let's take a crack at it. So let's first draw the NOR gate first. So NOR gate will have two P MOSFETs in series on top and two N MOSFETs in parallel. Okay, and then again, we're comparing this to a minimum size inverter that has 1x and 2x size. Okay, so here, because the N MOSFETs are in parallel, we can keep them at 1x size. That'll give them the same sort of resistance as a minimum size inverter. But because the PMOS gates are in series, we have to make them twice as wide to have the same drive because they're in series. So these each need to be 4x size. Okay, so that's the sizing we start with. Okay, and then G is the ratio of sort of this gate capacitance. So let's pick this one. Okay, so this is 5C, right? 4 for the PMOS, 1 for the NMOS. And again, the input of the inverter has 3C, 2 for the PMOS, 1 for the NMOS. So this G is going to be 5C over 3C, or 5/3. So remember, NAND 2, to input NAND, was 4/3 for G. That means the NOR gate is already, smaller Warset driving loads than a NAND gate. Okay, already, before we get too far. Okay, so now let's figure out P. Okay, so here, because we resized it, we have 1C for each of the N MOSFETs and 4C for the P MOSFET, so we end up with 6C here. Oops, 6C. And then we have 3C for the minimum inverter. So here we got 6C over 3C, which is 2. And this is the same as our NAND 2 was also 2. Okay. So if we were going to plot this thing, boy, do I dare do this? Okay, so D is end up being 5/3 H plus 2. Okay, so let's look at a case of this again, this now NOR gate driving 3 NOR gates like itself. Okay, let's look at that delay. So H, in this case, H is equal to 3. So D is 5/3 times 3 plus 2. So it's equal to 7. Okay, so it's 7 tau. And again, assuming it's our process, 180 nanometers, we said that tau was 11 picoseconds. Okay, so this delay ends up being 77 picoseconds for a NOR 2. And remember, we had 66 picoseconds for a NAND 2 and 44 picoseconds for a inverter. So it means that, yeah, go ahead.
Professor, can you tell me how about in the reverse line, not this one, the reverse one in the, let me see, with the inverse, how you compute a D equal 4D over there?
Oh, sure. So for an inverter, okay, G.
Because you just have one inverter drive 3 another, why you have 4 over there?
Gotcha. Okay. So the equation is, the delay is G times H plus P. Okay.
Okay.
So G is 1 and P is also 1. So D ends up being 1 times H plus 1. So D is H plus 1. So if H is 3, D ends up being 4.
Okay, got you.
So the other way to look at it is this plus 1 comes from the inverter's own output capacitance. This is another way to look at it.
Yeah, okay, thank you.
Okay, sure. Okay, so that was the 2-input NOR gate. Did everybody kind of follow that?
I just have a quick question about how you got 6 capacitance for the NOR gate on the right.
So this one here?
Yeah, I was just kind of lost how you got that. That's all.
Gotcha. Okay, so let's look at it. Maybe let me break it down. Okay, so if we just start looking at this guy, okay, it's 4 times, so this is basically what we have hanging off of this output node. This node here is we have this PMOS hanging off of that node, we have this NMOS, and we have this NMOS. The PMOS, we made it 4 times wide, compared to a 2 times wide, but anyway, it's 4 times wide to have the same resistance, so it'll have 4C going to supply. So that's the capacitance of the PMOS. Okay, and then the NMOS capacitance is 1C for this first one, and the second one will also have a capacitance of 1C because we kept them at 1x size. So we just summed these up, and it ended up being 6C.
Oh, okay, thank you.
Sure.
So why is it 5C on the other side?
Oh, because the gates, look at the gates we've got hooked up to. We had a 4x for the PMOS and a 1x for the NMOS. So 4 plus 1 ends up being 5C. And the equivalent for the inverter was 2C plus 1C, so 3C. That makes sense? It's kind of it's kind of confusing here, but just follow the algorithm is the advice I have for this thing. I mean, it kind of makes sense in the same sense that, well, you know, for a NAND gate, it's more complicated than an inverter. We have to increase the device sizes, so you can see how the delay is going to be higher than an inverter. And in NOR gate, we're putting 2 PMOSFETs in series. So PMOSFETs are slower than NMOSFETs. You have to make them bigger to get the same drive. So you could see how a NOR gate would be higher delay than a NAND gate. And then, you know, we go through this sort of process or this equations to come up with this equivalent delay. There's no, you know, again, there's no physics behind it that I can like tell you guys. Just, you know, I would just focus on how you come up with these numbers. Okay. Any other questions? Okay, so thankfully, like I said, these equations, okay, end up being the same, just depends on the inverter. I mean, sorry, depends on the gate type. For example, so here again, so, you know, this sort of talks about sort of stuff we did, all right? So how the input is the ratio of, this is for the NAND, this is for the inverter, this is for the NOR. So this G ends up being this ratio, okay? And so anyway, thankfully, unless, you know, I ask you guys to derive this during a test or something like that, anytime you have a appropriately sized NAND gate you know, if it's a 2 input, the G is going to be 4/3, 3 input 5/3, 6. It's dependent on the topology. So it doesn't depend on the process because you basically take these numbers and multiply it by the tau, the time constant of the process. Okay, and same with the NOR. 2 input NOR is always 5/3 for the G, 7/3 for a 3 input NOR, 9/3 for a 4 input NOR. So now it's kind of like you guys are seeing how bad things are getting as we are increasing the number of inputs for the delays, right? So this is like 2x. I mean, without even looking at the parasitic, is 2x the delay of an inverter. Okay, this is 3x the delay of an inverter as these sort of gates are getting more complicated. But if you had a NOR gate that was sized the same way as a minimum inverter in a 65 nanometer process or a 180 nanometer process or any process, the G would be 9/3, okay? And then you just multiply it by different tau for the process. So that's kind of that's part of the strength of this way of calculating delays. Okay, and the P, okay, is basically again the ratio of the drain capacitance to the normal inverter. Again, inverter has 2x, so there is 2 C's for this guy, and for this guy is 1 unit size, so that will have 1 C. Okay, so everything basically, once we redraw the sizes for another gate, we divide that drain versus this one. Okay, so again, we have for P's, we also have, regardless of what process we're at, and as long as this thing is properly modeled, we can use these numbers, okay? And again, if you look at this NOR4, right? So the delay of this NOR4 was, what did we say? We said it was 9/3, that was the G from the last table, times H plus 4. And the delay for a 1, so this is 3H plus 4, okay? So the delay for a inverter, if you guys remember, was 1 times H plus 1, or H plus 1. And you can see how much slower a 4-input NOR gate is than an inverter. So that's why also it's kind of telling you, if you want to go fast in CMOS, you really want to sort of keep the number of inputs in your stages low to go fast. Okay. Okay. So here, let's do another example. So let's do this together because this is the kind of confusing. But you know, if you have a odd number of inverters hooked up together, and it has to be an odd number, okay, because you want, when this thing starts, you want this to be 0, you want it to like go to 1, 0, ripple all the way through with a certain delay, and then here, then it turns into a 1, and then so if you look at the output of this guy, it's going to be oscillating. It's probably, well, depends on how many stages you have, but it'll just self-oscillate at a particular frequency. Okay, and the particular, people use this all the time, this ring oscillators, for looking at the behavior, like the speed of a process, because this delay is fairly long because you're going through 31 delay stages, okay? And then you even have to, because you have to invert again, it's like 2 times 31. So this is, let's say if this was a 31 stage, you would have this period would be times 2, because you'd have to carry a 0 across and then come back with a 1 across before you get to 0 again. So if you look at the period, you'd have the delay of 31 stages times 2. Okay, so it'd be a relatively low frequency that's easy to measure on the lab. Okay, because this would be, let's say for a, I don't know, let's say it's like for a 180, I'm just guessing, for a 180 nanometer process, let's say this ring oscillator frequency would be, say, 300 megahertz. Okay, now imagine if I just had the ring oscillator with 3 stages. Okay, that would be 11 picoseconds each times 3 times 2. So it'd be 66 picoseconds. So that would be, what would that be? I'm gonna guess that's somewhere between, that's obviously somewhere between 1 and, well, let me just calculate it. It's fast though. Let's see. Okay, so my calculator is telling me this would be 15 gigahertz. That's hard to measure. I mean, it's just like, that's a hard thing to deal with in the lab. So if you have a 31 stage oscillator, you end up with a number that's like easy to deal with, to measure it. And you can get an idea of the delay per stage of your process. Okay, so let's try to use this logical effort to figure this out. Okay, so this methodology for delay. So the logical effort, otherwise known as G. Okay, so we have inverters in this case. Each stage is an inverter. Okay, so we go look up the G of an inverter is 1. Okay, so G is 1. The electrical effort is H, or the fan out. In this case, each inverter is just driving one inverter, another inverter like itself. So H is equal to 1 as well. Okay. Now the parasitic delay, again, it's an inverter. We go look back at the parasitic delay, and that ends up being a 1. Okay. And so the stage delay, D, is GH plus P. So it's 1 times H plus 1, or, so H, sorry, H is 1 also. So sorry, that's 1 times 1 plus 1, so is equal to 2. So that's the delay per stage here. Okay, so if you want to find the frequency, like I was saying here, the total delay is N, that's the number of stages, times 2, because we have to first put a 1 across and then a 0 across. So first you have to push a 1 across and then a 0 across to get the full period. Okay, so that's where the 2 comes from, times 2 for this delay per stage. Okay, so it ends up being 4N. And so the oscillation frequency is 1 over TD is 1 over 4N. Whoops. Or 1 over 4N tau, if you want to come up with a number. So let's say if you had a 31 stage inverter, N would be 31. And let's say it's in a 180 nanometer process, so tau, which I sort of had this approximation of 11 picoseconds. Okay, so what is that? That's 62. The t delay is 31 times 2. No, wait a minute. Sorry, guys. We already had all that included in this. So the time delay, t delay, is equal to, what's this guy here, is 4n tau. So it'd be 4 times 31 times 11 picoseconds. Okay, and that is, so 431. Okay, I end up with 1.36 nanoseconds. So the frequency is 1 over that. Or 733 megahertz, assuming I have that right. Oops. So this is a 0.6. So let's do it with this one. So this was, if you guys remember, sort of the second stage. What was this? This was 60 picoseconds, I think, for a single stage. So if we do that same thing, we would end up with F for, in the 0.6 micron process, it would be 1 over 4 times 31 times 60 picoseconds is what I remember. So let's see if I remember that correctly. Well, I end up with 134 megahertz. So not quite right, but I don't know if I'm remembering the right thing for the, let me just double check this. No, it is 60 picoseconds. So we're off a little bit, I guess. But anyway, so that's sort of how you come up with the delays. Did everybody see what I was doing? That makes sense? Okay, so let's do another example if I can only get here. Okay, so here's a case of a fan out of 4 inverter. Okay, and so this fan out of 4 is kind of a magic number. A lot of times we, like if you see data sheets, etc., they give this fan out of 4 number as a figure of merit, because it's like sort of a typical thing. It's like, typically one gate is driving 4 other gates, or it's not unexpected that would happen. So they use this fan out of 4 as kind of a popular delay. Okay, so I'll give you guys, why don't you guys give it a shot at this one too. I'll give you guys a minute to try it out before we work it out together. Okay, guys, let's try to do it together now. So let's see. So the logical effort is G. Okay. And if you remember, so we got an inverter. So I just happen to remember from our table, or you can look it up, G is 1. Okay. The electrical effort is H. So that's the fan out. In this case, we're driving 4 other inverters like ourselves. So H is 4. Okay. And I remember the parasitic delay P for an inverter is 1. Okay. So the total stage delay is G times H plus P. So that's 1 times 4 plus 1, or 5. Okay, so the absolute delay of a process for this
Professor, are you writing anything on the board right now?
Oh, yeah, I was.
We can't
I
see.
think I lost. Thanks for chiming in. Every once in a while, I lose a link with my iPad. This is so much fun. Do you guys? Let me do this. Sorry. Let me start. This whole Zoom thing is a lot more complicated than I was hoping for. It turns out that your iPad session can't record video in Zoom. Only the Mac or PC version can. And if I use it on my Mac or PC, then I can't really annotate too easily. So anyway, it's all fun. So anyway, so let me rewrite this thing. So G is 1, okay, because we have an inverter. And just looking at the table, I just remember G is 1. H is the fan out. So we got 4, driving 4 stages like ourselves. So that's 4. And parasitic delay, because it's an inverter, is just 1 again. Okay, so the total stage delay is G times H plus P. Okay, so it's just 1 times 4 plus 1 equals to 5. Okay, so if you're looking at the absolute delay of a fan out of 4 inverter, which is kind of a figure of merit for a process, is 5 times tau. Okay, so for example, in our case, it would be around for absolute for 480 nanometers would be 5 times 11 picoseconds is 55 picoseconds. So this would be this delay from in to out. Okay, so you know, I'm not going to go into. Unfortunately, we don't have time to go into the next step here, which is figuring out the is a multi. You know, doing the same thing. So this is capital G, capital H, capital F. For a multi-stage network. That's where things will become like pretty useful now. Because one stage, well, it's interesting, but if you have a multi-stage network like this thing, okay, now this is like a bigger problem to solve. And this is sort of going back to our decoder, right? So we had multiple stages, each one was driving something else, and everything is dependent on everything else. We have external load, and we have sort of an internal input capacitance, and then we want to figure out how to size these different stages, okay, given that we know what functionality we want. Okay, so that's what's coming. But because it's sort of starting a thought process, I won't start that, but let's just say like there's a couple of caveats, and like one of the bigger ones for using this methodology, using this logical effort methodology. The biggest assumption we're making, and we'll probably see this in our projects is that the input, and this is the biggest, also the biggest assumption we took in the case where we were using the resistors and capacitors. Okay, we assumed the input rise fall time is very fast. Okay, so what we're looking at is, if I draw this in the time domain, we said, you know, so the input is transitioning, whether it's going high or low, it's rise time. So meaning this guy is very, very fast, like infinitely fast, a picosecond rise time, whatever. But as this thing has this rise time, let's say you're being driven by another stage, maybe like yourself. So your rise time is going to look like more like, you know, have some slope, right? And then that will affect the transition of the next stage. Okay, so this is the biggest, in my opinion, this is the biggest difference between this and what you'll see in simulations, is this effect of the rise time. And we'll see, I think we'll get a chance to talk about how we can make up for that. Okay, guys, so I think I'm going to stop here because, again, we're going to get to some pretty complicated things with multi-stage networks. So this is a good stopping point. And email me if you guys have any questions. Sorry about the technical difficulties. And hopefully, you know, I'll have everything up in the Blackboard, and hopefully we'll smooth this process up.
Professor?
Yeah, please go ahead.
Where are the recordings going to be for the lecture?
Good question. I think I'm gonna keep them on YouTube and put a link in the Blackboard so you guys can link to it. There's a couple of other places, and the university's kind of sending warnings about not everybody's going to Zoom, various weird things are happening. So if there is a difference, I'll let you guys know. But there should just be a link that you guys can click on and go to on Blackboard.
All right, thank you.
Sure. Any other questions, guys?
Yes, I just wonder, are you gonna putting the handwritten note, this one on Blackboard also?
Yeah, I'll put that up as well.
Thank you.
Sure. Okay, guys, if there's no other questions, take care. I hope everybody's staying safe and productive. And I guess we'll talk after the break. Bye.
Thank you. Have a good weekend.
You.
Thanks.
Have a good spring break.
Have a good break.
Bye.
Thank you. Have a good break.